I'm going to be taking away the sheet at 10:45, so sign in now if you haven't. Your name's Ashutosh Mohit. What's your name? Preeti. Okay. How's it going with the panorama stitching homework? Okay. What about you? Yeah, that's fine. We already did the grayscaling in the first one, right? So you already know how to do it. So it's fair to use whatever now. Uh, no, I'm not leaning towards having you guys memorize anything because it's useful to understand intuition of formulae, but when you're applying them, well, typically it's in code, and as long as you know what you're doing, you don't really need to memorize the formula. So if there ever is a situation where you would need the formula, then you would just look it up in practice, right? So I don't expect you to memorize formulas. Um, if there is anything numeric in the final exam, um, and if the formula is something complex, then I'll provide it. Simple things like if I expect you to normalize something, that's usually subtracting the minimum, dividing by the maximum, things like that. I may skip the formula, but anything that has Greek in it, I'll provide. The volume at which I was talking right now, were you able to hear that? Okay. One of the pieces of feedback I got is that I speak softly. Uh, so I bumped up the volume a little bit on the mic. I don't know if that's helping. I kept it pretty low earlier because there's a very slight delay between me speaking and what comes on the speaker, and that throws me off a little bit. But okay. Uh, I think this is on. I can't tell if the mic's working. Yeah, I guess it's working. Uh, okay, yeah. So I'll leave that the way it is, and I think that should be fine. And then I also got this thing, so this should help me walk around and not be tethered to the laptop, and maybe help me make it more engaging. I'll try to put a bit more energy into it. It's hard when I have to talk about math. I don't really like math. The panorama homework, I'd suggest getting started on it sooner rather than later, because it is. I mean, the idea is not very complex, but the implementation, it's tricky getting it right. Uh, you will Odds are you'll be able to stitch two images together, but then when you try to stitch all five of them together, you might end up with one image not getting stitched in the right place. Um, And even the way that they all get stitched, it might be the case that one of them is warped a lot and the others are not, and they're all really far off in the distance. One is very close. uh, as long as you're able to stitch two images, I'd say that that's valid, but ideally, just for uh, your own satisfaction and um, peace of mind that you did understand everything and you're able to do it right, aim for all five. Definitely, it's it's a bit challenging, just a little bit. You had trouble with lockdown last time, right? Did you? Worked fine. Okay. From what I remember, it was people using Macs who had issues with lockdown. Okay. There's going to be a quiz today. I'm just putting that out there. Uh, I brought a few printed copies. I think I have five or six because I think last time about three or four people had trouble. Um, yeah. Pranath? No, just check. Your name's Pranath, right?
Yeah.
Okay. Morning. Pavan, your name is Sandeep? Okay, I'm just trying to memorize names. Okay, I guess that's time to start. We're going to pick up where we left off last week today. Last week, we talked about machine learning in the context of image processing a little bit. So one of the things we looked at was the softmax function, which we use to squish our outputs to between 0 and 1. This is useful when we're doing things like classifying, because we want our outputs to look something like that. That over there is a probability distribution, and you can see that the values are all between 0 and 1. And in this particular case, whatever highest value we had going in there, so here we had a 7, which was the largest one. Once that goes through the function, we calculate the value of e to the power whatever value we have in our output logits, and normalize that with respect to the sum of the exponent of all of those. That rescales all the values between 0 and 1, and we find whatever is the largest value is what the model predicts as a likelihood for the class. When we're picking one, we can also pick top 3, which is something that you'll see in older implementations of YOLO, where you have an image of, say, a Bengal cat, which kind of looks all similar to a big cat. So you'd have multiple probability values that are close to the highest. We're able to apply that when we have a multi-class sort of formulation. Whatever models we use are typically combinations of weights and biases along with input variables. So adapting the previous equation that we had for this particular scheme, where we're dealing with a system of matrices, we plug in a few variables over there to account for there being weights and biases, but it's more or less the same expression. We're still doing the same thing, taking individual logits and normalizing them with respect to however many logits we get. And that tells us the probability of getting a prediction, a class, given our set of input variables and the index of each weight. So that works out to this when you expand the whole thing. So this is when we have 3 input variables and 3 classes. So there's 1 weight for each class corresponding to each variable. And there's also a bias for each variable, which goes through the softmax function, and we get individual outputs at each output of the model, whatever the model may be. So one of the cases that we looked at was recognizing handwritten digits. We did this using a regression model, and there were 10 classes. Each of these is a 28 by 28 image, and we flattened those, put them into a linear model, did regression to find an optimal set of weights, and that lets us classify it with pretty good accuracy. We also looked at support vector machines, which allows us to improve the kind of linear models that we get by maximizing the space, the margin between our 2 classes within the whole distribution, because we could have more than one line. We could have one going like that. We could have one going vertical, but we want to maximize the margin. So we do that by adding support vectors and maximizing the distance. We also looked at detecting people. So here, the Laland Triggs, their algorithm involved extracting hog features first, which gives us an idea of what a person would look like in an image using the orientation of gradients, and apply that at multiple points along the image, kind of like a sliding window based approach. That had a lot of computation, so to make that a bit more efficient and also more precise, we injected some of our understanding into it by doing it at multiple resolutions. So a low resolution feature map was enough to find an approximate location of where a person would be. And then we use a higher resolution map to look for finer features, which was a parts model, where we know what individual parts of the body would look like and their relative positions. And we're able to do both of those things, learning appearances of individual parts and also where they would be located relative to each other using another SVM. And we also introduced the concept of hard negative mining, and the term comes from hard negatives, which is your negative classification, negative samples that are hard to identify correctly or differentiate between what we're looking for versus what we don't want. So we prioritize those ones higher because they're easier to get wrong and harder to fix. So we didn't get into the current modern day paradigm yet. It's not much of a spoiler for me to say that pretty much everything we do today is uses neural networks in some way, but before that was a thing and before people were comfortable with the idea, the state of the art used to involve feature extraction as its first step. So a rule-based approach where we had to guess what might correlate with what we're looking for in an image. Those could take the form of SIFT features, which we've seen earlier. There's a whole bunch of other features that have been used historically. There's orb, surf, hog, and then there was also the implicit assumption baked into that approach that the sample space would be linearly separable. So when you're dealing with 1,000 classes, trying to separate your sample space using lines is kind of involved, not really practical. So a few things that we would like to improve here ideally is that our feature extraction, if we can do that automatically, that's great. And if we can do better than lines splitting our sample space, that would be even better. So in the interest of just building excitement for why this is useful and why we're spending time learning this, following the paradigm shift, our baseline expectation when it comes to classifying a set of images for 1,000 classes has gone up to 90% from the 50s, which is what we used to see with linear SVMs. And even for object detection, we're able to do it significantly more accurately. So today we will dive into neural networks. I want you guys to tell me what you think a good way to model this would be. To guide that process of reasoning about this, can you separate this with a line? What would be a better way to model that than a line? You know what we're supposed to be doing, but just simply visually, geometrically looking at that, well, what shape splits that? Well, I heard someone say louder. Yeah, so one class is in there with a whole bunch of points. There's the other class that's outside, and we can draw a circle, and that would split that pretty well. Now, our models, we can't draw circles, but what we can do instead is move our samples around a little bit. So instead of looking at the relationship between y and x, if we look at the relationship between x squared plus y squared and x, that lets us draw a line between it and separate them. So what we're doing essentially is reprojecting whatever samples we have to a higher dimensional space that allows us to then separate our samples more easily. So feature engineering, a lot of what we do with what features we choose when we're doing the older style involves baking in some of these transformations into the data pre-processing pipeline. And that requires our understanding of what the distribution is like and some sort of a priori expectation. And our linear model that we've been dealing with so far is typically whatever input variables you have with some weight and maybe a bias, and then we look at a linear combination of those to get a prediction, which essentially gives us lines. So it's not very good for the kind of problem that we're trying to solve, since our sample space is a bit more complex. So how do we go around that? We can add some processing to it. So far, we've just been doing linear combinations. Instead of that, instead of directly getting a prediction, how about we add some extra computation that sort of approximates reprojecting it to a different dimensional space? We do this this is our first step towards a very basic, very simple neural network. We have our input variables, and these constitute a hidden layer. So we changed the relationship a little bit. We no longer have two variables going to one. Instead, we're projecting it to three variables that mean something implicit. We don't know what they represent necessarily, but this is still linear combination where you have weights associated with each edge. So x1 going to h1, you would calculate using the weight w1, and then x2 also contributes to whatever value ends up in h1. And that amount of contribution is governed by the weight associated with that edge, and similarly for the other neurons. And outside of the weights, there's also a phi over there, which is some arbitrary activation function. So when we talked about activations earlier, we looked at just using a naive threshold. So if it's above 0, we predict a class value 1. If it's below 0, then we predict a class value 0. So something like that. It doesn't matter what it is over there. And since it's still in a similar format to what we've been dealing with, the cool part is we can express it as a system of matrices. And we love matrices because GPUs love matrices, and matrix operations are really fast. Then we can use our reprojected sample space to make a prediction with another set of weights. So you're essentially learning a representation of your inputs that is hopefully easier to separate, and then projecting it back down into your prediction space, which is however many classes you have. We can conceptualize what's going on over here by saying that this part is extracting features, and this part is still doing whatever our linear models have been doing so far, whether that's regressing a value or outputting probability distributions for however many classes you have. Whole thing is matrices. Matrix operations are fast. And that is the most basic example of a neural network that we can have. These are, depending on what time period the literature is from, you might see them called as feed-forward networks, as multi-layer perceptrons, or just a fully connected neural network. Each of these is a neuron that has some activation function associated with it. And the reason that this is how it's designed is that it takes inspiration from how the brain works. In the brain, when you receive some stimulus that goes through whatever sensory pathways, so if it's your eyes, will go to the retina, optical nerve, to the visual cortex, and over there, depending on whatever you're seeing, different neurons will react to it, and that can be modeled mathematically as activation. So if you have spiking potentials in the brain that are higher than a certain threshold, then that activates the next neuron that's in the same neural pathway. And this layout is designed to mimic that process. So putting all of it together, we have a whole bunch of weights at this point. It looks like there's a lot of terms over here, but it's not complicated, really. We just, to get P, you need to know what H1, H2, H3 are. To get H1, H2, H3, we need to know X1 and X2 and how much they're contributing to each of those. So there's products of those, which we then substitute in here. And that way, for an arbitrary number of layers and neurons, we can calculate what the final prediction at P would be just by chaining all of these weights together. The cool part about adding an activation function is, so I didn't go into the detail of what activation function we're using. I just mentioned the example of the threshold that we looked at earlier. If we use something like a sigmoid or tan H, which I'll show you graphs of those a few slides later. The cool part is that allows us to do nonlinear things. And the example that we saw earlier of the space that could be separated with a circle, that when we project it to a nonlinear space, we're able to separate it. So introducing nonlinearity allows us to represent more complex functions. And without nonlinearity being introduced, no matter how many layers you add, no matter how many neurons, you would still only be able to approximate a linear function. The reason this idea is so powerful is, and also the reason I've been trying to have us think about everything in terms of functions, is the origin of it is from Sybenko and Hornig, 89 and 91. They came up with the universal approximation theorem. And while there's Greek there, what I want you to take away from this is basically you have an arbitrary, really small epsilon, and you have a real function that you want to approximate. Say it is, if you want to predict where, you guys know the thing where it's like a demonstration of normal distributions. There's all these little ball bearing kind of things that you drop in a board that has a lot of pegs on it, and then it keeps going through them, and where it ends up at the bottom mimics the natural, the normal distribution. So you would be able to model something like that, as we know what the function for a normal distribution is, right? We'd be able to approximate something like that, where this is what the actual function would be, and this is our approximation of it, which is a combination of weights and biases. The difference between that would be close to zero. And you can do this for any complex continuous function. Complex, I don't mean it in the imaginary numbers complex sense, but just complexity of the curve. So the idea, the implication of the universal approximation theorem is that you can, anything that follows some sort of law that can be expressed as a hypothetical function can be approximated by a neural network. The terms in there, we have the actual function that we would like to approximate, and this we can set it to whatever arbitrary limit of accuracy you want. The smaller you set it, the tighter your expected approximation will be. And you do this for all neurons. B is the bias, A is an arbitrary constant. There's weights, the activation function, and this whole term is the output of the neural network. So the big implication or ramification of this is that in theory, a single hidden layer neural network can approximate any continuous function with phi as an activation. But in practice, a single layer isn't usually how things are done. Depth has proven to be a lot more effective than width. And there's limits to what we can learn. And universal approximation theorem doesn't really go into specifics of how we model things, just that it can be done. The reason we care about this is because images are numbers, which means we can plug it into neural networks. What would that look like? We can assume that for an image of a handwritten digit, there's some function that maybe someone clever could come up with after spending a lot of time on it, or we can approximate a hypothetical function that recognizes what digit is written. Now, if we had to try to approach this in a rule-based way, it's not trivial to do that, because how do you start saying that? Well, if there's a horizontal line followed by what someone could write that with a curve, someone could write that with an angle. So it's not trivial to do that, but there could be some combination of rules that, if you're comprehensive enough with it, will tell you what class you have. So instead of trying to figure out what the rules are by ourselves, we let a model do it for us. So we start by flattening it into rows and stacking them one after the other. And that's how many input neurons we'd have. So it's a 28 by 28 image, which when flattened becomes 784. So you have 784 input neurons, which go into however many layers is appropriate for the problem. So over here we have 2 hidden layers, followed by, this is 10 neurons, because we have 10 digits that we want to bucket each image into. And with some hypothetical ideal combination of weights and biases for all of these layers, it stands to reason, following the universal approximation theorem, that we would arrive at something that lets us predict what the right value is. A way to sort of conceptualize what might be going on under the hood, looking at images of handwritten digits, we could break it down into smaller problems where you break down trying to identify a 9 into trying to find a loop up top followed by an edge. 8 can be thought of as 2 loops. Similarly, for a 4, you have a combination of a long edge, a short edge, and a horizontal short edge. That can further be broken down into smaller features that we look for. So you can think of what's going on over here as it takes this whole input, which is the flattened image, and learns how to find little features from within what we supply to it. And it progressively gets finer the deeper you go in a model. So if you added another hidden layer over there, it would potentially learn features that compose the features in the preceding layer. Now, up to this point, what we do know is what the structure of our neural network should be, what it's comprised of, which is weights and biases. But what we don't know is how we get the values of these weights, because if we don't have good values of weights, what our model predicts will be gibberish and of no use to us. We've already been exposed, we're acquainted with gradient descent. That's the weight update rule. Neural networks, for our linear regression, when we talked about it, we started by going over the closed form solution, which let us calculate it by inverting a matrix. But for neural networks, there's no closed form solution. So the only way to find a good set of weights is through optimization. So for that, we apply gradient descent. The prediction that we get out of the model at P is now your weight, and we're factoring in a learning rate. And this comes from the gradient descent weight update rule. And combining that, what we end up with is your new weights or the old weights plus learning rate times difference between what was predicted versus what your actual value should be. So that's y over there, and this is our prediction. Essentially, what we're doing is comparing what we know the output should be with what our model spits out and estimating the error. And then we look at the gradient of that error, which is a loss function or likelihood if we're maximizing something. And we use that to inform our decision of how to change weights. So the way you can do it is either start with completely random values for all of the weights, or there's more, there's clever ways to do it, which are named after the people who came up with them. There's Xavier, there's a couple of others, and they're all baked into whatever frameworks are commonly used. But we use this to adjust our weights, to nudge them every time. So what we know at this point is what the expected label is. And in this case, we start out with two input variable values. We have a 10 over here and a 1. And the value that our model at the moment with the given set of weights, whatever they are, what it's predicting is smaller than what we would like. And we want our predicted value to be larger. So how can we adjust our weights? Do we make our weights larger? Do we make them smaller? There's only two choices, really. 50-50, these are reasonable odds to throw out a word and have it be right. Yeah, we make our weights larger. So your weights get multiplied with whatever's in there, right? So if you have a weight of, say, 0.5 each at the moment and you double both of those, then your initial output would have been a 5 going there plus 0.5. So from 5.5, you go up to an 11. So the value gets larger. whatever changes we make will affect the 10 neuron more. Expanding the whole thing a bit more, the individual weight updates, it's the same formula applied to both of those. Eta is the learning rate, input variables, y is true, error, and this is what we're using to say that our P should be larger. Once you plug in these values, it becomes evident that whatever changes in weights we do are proportional to the values that we find initially over there. So changes that we make informed by our error will result in W1 having a bigger change compared to W2. A full example, so to do the forward pass or forward propagation of our inputs through the model is effectively unpacking all of these weights and adding them together. We start with input values of 2 and -1 and look at contributions of each of those to H1, H2, H3. So 2 times 3, and then H1 also has a contribution from -1 with a weight of W2, which is -2. So 2 times 3 plus -1 times -2, we end up with an 8 over there. Similarly, we calculate the other values for H2 and H3 and use those as our input values to calculate P. So we have 8 times the weight for this edge 2, which is a 16. You have -30 over here and a -7. And putting all of that together, we end up with a -21 over there. So for a full neural network, scaling it up for multiple neurons, we calculate the activations at every neuron and rewrite the whole thing as a system of matrices where we can put all of our weights in as coefficients for all of our neurons and take a weighted sum. Also add in a bias vector if you're using biases, and wrap that whole thing in whatever activation function we're using for that layer. So essentially, it's still the same thing. You have your weight times your input at whatever layer, and add a bias to it, wrap it in your activation, and that gives you the output of the next layer. So to modify these weights, we know that we want our P to be larger based on the error between what our model predicts and what we know it should be predicting. So we use that to inform our decision, and we propagate that information backwards through the network. We do this using the gradient of the loss. The math for that is a bit involved. So I'm not going to be going over the backpropagation algorithm. It's beyond the scope of a vision class, and I think a deep learning class would cover that, or a machine learning class would already cover that. But the essence of it is that depending on the sign of the gradient, that tells us what direction we should be nudging our values in. So if you have something that is negative, then you don't want that to be as negative, because the final output that you want is supposed to be increasing rather than decreasing. So contribution from that would go down. Contribution from the positive terms would go up. So this would ideally cycle over from negative to positive, and this is already positive, so it should get bigger, and this should get smaller. And we do the same thing going backwards until we get back to the first layer. Doing that, so this is a hypothetical in-between state, an untrained model, and what it's predicting isn't what it should be predicting. So we know what the loss values, whatever metric is being used. So here it looks like it's the squared error that's being minimized. We compute that for each of the outputs with what it should be and sum the whole thing together, which gives us a total loss value. And then we use that to nudge each individual weight. And eventually, we get to a point where the total scalar value, which was the sum of all of these, doesn't get lower any further. And that's when you say that your model is trained, your model has converged. And we end up with a reasonable approximation of the function that we went in with trying to approximate. Essentially, we are looking at how the loss is changing relative to the direction of changes that we make to weights, and it's a feedback loop. We do this using the chain rule to calculate partial derivatives and propagate that information backwards. The example that we looked at so far, there wasn't any complicated activation going on at any of the neurons, but we can sub out whatever simple activations we've been thinking of so far with more complex ones. To put the whole thing together, we do a forward propagation, which gives us a prediction. We compare that with what we know it should be spitting out, propagate the errors backward, and update our weights and keep doing this iteratively, which would allow us to model even something like that. Now, this, while it splits that distribution very well, this wouldn't generalize necessarily when you add more points, because those are better thought of as outliers, and neural networks are arbitrarily powerful. So they might end up overfitting to a distribution or underfitting, where it doesn't model the distribution really well at all. We want a happy in between, which is a point that has a good trade-off between bias and variance of the model. So we need ways to do that, to pick a happy medium. And that brings us to two things. One of them is regularization, and the other is boosting. Now, we talked about boosting in the context of the Viola-Jones algorithm, where we had several weak classifiers which we combined together to effectively act as one strong classifier. We can make a bunch of weak models and put them all together. That's boosting. Or we can penalize our model for fitting too well. We rein in their power. So for SVMs, we added a condition for that allowed it to accept a few outliers, which was the soft margin version that we talked about. For a new neural network, one way to do that would be, in addition to minimizing the loss function, which is the difference between our predicted values and what the actual values are. We also penalize the sum of weights from so that it doesn't get too large. We put another term into what we're minimizing so that the weights don't keep exploding. That is called regularization. One common way to do that is using the L2 norm, and it's called weight decay. So what happens is with every iteration, every time you, even if it's a weight that hasn't changed in that particular weight update, it will decay a little bit. It will get smaller by a tiny bit. So that keeps everything moving and the network alive in a sense. Another cool trick. So at this point, we're assuming that we're able to arrive at a solution that is a good trade-off between bias and variance, but it's taking us a really long time to get there since we're doing it one gradient descent step at a time. Now, when we're doing gradient descent, we know the direction that we're moving in every time. And if we see that we're moving in one direction, we've been moving in a direction for a few steps and it still seems to be the way to go, we can just go faster in that direction. And this is a part of a lot of optimizers, whether it's gradient descent, whether it's Atom, there's a whole bunch that you will come across when you actually start fiddling with these. That's called momentum. So we can assume that if we're heading a certain direction by changing our weights, that odds are we'll find a minimum in that direction. So let's just go faster. And we do that by adding a momentum term, which takes the previous weights into consideration and looks at the delta between then and the current one. A side effect is that if you have gradients in different directions, it smooths out the updates, but that's not something that will probably make a lot of intuitive sense until you actually do it and look at your loss curves. Putting everything together, we now have weight update rule that also incorporates momentum and weight decay. And that is how we train a neural network. So we look at the gradient of the loss, the weight decay, momentum, and there's the learning rate. And all of this together is what we use to change our weights. So I mentioned activation functions that we deal with more than just linear activations or simple thresholds. These are a few activation functions that are used commonly to introduce nonlinearity. We can use the logistic tanh rectified linear unit or leaky ReLU. This has been really popular lately. There's a whole bunch of others, and there's a lot of literature on which of those is suitable for what task or what architecture style. You figure those out with experience. Now these hyperparameters are, well, these are tunable values that we decide while training. So for all the automation that we're doing in terms of what features the model learns or what good set of weights would be. There's still a few values that we have to pick, and this is, I've been basing my slides off Dr. Redmond's slides, and he's the guy who came up with the YOLO architecture, really cool paper. So this is directly from his slides. He also came up with the framework in which he trained his first YOLO model, and that was called Darknet. And this aesthetic is a signature of his, so I figured I'd keep it as is, just as homage, I guess. Good set of learning rate values that you find in the wild typically fall within this range. There's also weight decay, which is typically this value. Momentum is also almost always that value, and leaky ReLU has been the activation function that most new implementations default to. So this is verbatim from the big man himself. I've added links to, so a lot of these visualizations I put in here, these are from 3Blue 1Brown. He has the whole playlist going over neural networks from scratch, including backpropagation and the calculus for that. If you're interested, you can go and check out the playlist. But I don't expect you to know backprop, and I'm not going to ask it on an exam. Filtering that we looked at, whether it was to find edges or whatever, we were able to use convolutional 3x3 kernels to do a lot of those things. The values that we put in our kernels, so in the case of Pruitt or Sobel, those were values that those people came up with, and they figured out that those values are good to find whatever features they were designed to find. What we've been doing is learning weights, right? So what is a kernel? You can think of it as a bunch of weights, and that means we can learn what values to put in convolutional kernels by treating the whole thing as a neural network, which allows us to automatically create whatever filters are useful to solving the problem. And these are the kind of feature maps that you end up with at different layers within a real deep neural network. What these correspond to is kind of hard to say just by looking at it, and that is that holds true. The deeper you go, it gets more abstract, but this correlates with whatever objective the model was trained for somehow. And we're able to combine all of these to get a linearly separable classifier at the end. We will be looking at CNNs next class. For now, what I want you all to do is fire up your Lockdown browser, because we're going to have a quiz. And if you have issues with Lockdown, I'm hoping it's not more than 5 people who have issues with it, because that's kind of the number from last time. Wait, hang on. 1, 2, 3, 4, 5, 6. I have 6 printed versions of the quiz for those who have trouble with it, but everyone else will be using Lockdown. And you probably can't see it yet because it's hidden. I'm going to make it visible in a second. This doesn't cover any of the machine learning stuff yet. It's till lecture 6. I just made it visible. See if you can open it. and I will give you the password for that shortly. Show of hands, does everyone have the quiz up? Are you able to see it? I would like to see hands, please. Quiz, is it up? Is it asking you for a password? Do you have lockdown working? Okay. If you don't have lockdown working, hands, please. Okay, I see one. Anyone else? You have a pen on you, I hope, because I only have the one. I can give you mine, but if there's anyone else who needs it, then we're out of luck. That's the password for the quiz. To get access, it's Kanadi, and to finish early, it's Lucas. You may start whenever you like. You have 20 minutes. There's about 20 questions. It's not an exact 20, but it's worth 100 points. And I don't think anything should be too challenging in there. I'll give you a print. Okay. You need one? What's up? Uh, yes. You can close this. Go back to your UV lamps. Don't open it directly. If you open it from the quiz, it should. Just look around. Give me your phone. Your phone, please. Yeah. I wanted to come to my office. I wanted to come to my office after class. Just stay with me. we're done with the quiz and want to talk about the project, I'll wait here for like an hour. You can take a seat up front while everyone else finishes. And once everyone's done, we can talk.
So the final will be the same format as the quizzes, so this will be
A little bit of these quizzes, a little bit of the written homework, a bit of both.
yeah, but that will be on everything will be on the
Lockdown?
lockdown.
Yeah.
Or it will be some like handwriting questions.
I haven't decided yet. Lockdown is what I'm leaning towards. But if you need to do calculations, I'll give you a scratch paper to do stuff.
Okay, but like all the answers submitted on the browser.
Yeah, that's what how I'm thinking of doing it at the moment.
Okay, so it's not just the multiple choice questions, but it's going to be some like summary.
I mean, the final answer that you would pick would still be more or less multiple choice, except for maybe a couple of ones where you'd have to like type in a number or something.
Okay.
But I'll try to structure it like that.
Okay. Great. Thank you.
Yeah.
The feedback of project.
Okay, can you wait? I just want everyone to finish. I don't want to disturb people. They're all waiting to talk about the project. Yeah. Can you come outside? Okay, sorry about that. Everyone done with their quizzes, I hope? Okay, yeah. Okay, yeah, thank you. About the project, who wants to go first?
Feedback here.
Hmm,
But these suggest a different use case from what I was proposing.
okay.
So here they are going through the traffic scene and then detecting if the driver is going towards the passenger or not.
Okay, yeah, I didn't like go through them in a lot of detail. If you
Okay.
think they're not relevant,
But
you're
I
free
wanted
to ignore them.
work on these kind of things. So I want
Hmm.
to monitor the driver's face and then see the extent of his eyes being closed and if he's yawning, and then I also want to perform
Hmm.
some background segmentation so that we don't detect facial expressions of the one sitting behind in the vehicle.
Hmm. So the can I go back here?
Yeah.
So
These
this
papers are
thumbnail,
yeah.
are all of them?
Yeah, these are all monitoring the traffic scene, not the driver.
Hmm. Okay. Yeah, in that case, what feedback did I give you? I don't remember.
Yeah.
Uh,
So actually, for the system I am
was-
proposing, there is no state of the art, but there's a very good research done by Qualcomm.
Okay.
That was application, but not a paper. So I haven't mentioned it there as state of the art.
Yeah, in your next report, just include that also. As long
Yeah,
as
I'll
you're
definitely be
confident.
proposing it.
Okay, yeah, maybe like put visuals from it or something like that. Because I mean, like 30 people, all of their references, it's a bit hard for me to. Okay.
Yeah. So this is one Qualcomm.
Mm.
But this is way too advanced. I'll display performing background segmentation over here,
Mm.
and I'll check these things are similar. But here I think they're checking the angle of the nose, but I'll be estimating the pose of the entire body.
Why?
I want to see if he's leaning forward to detect.
Okay. Okay. Yeah, go ahead with it. Sounds good. Yeah, as long as you're confident about whatever literature survey you've done and you know that no one's already done that, then it's fine. Yeah. Yes. Hi.
Project was an image deep learning using deep learning techniques. So,
Okay.
yeah, and you wrote a suggestion to check if that improves object detection.
Let me try to find yours. Yeah, you can just help me find which one is yours. What is it? What's your name?
Swapnil.
Yeah, okay. Deep learning. Mm. Mm.
Face recognition. So,
Yeah, I mean, deep learning on its own, the state of the art, I think it's already fairly advanced. And if you're doing just deep learning, then you'd have to do something different, right? And whatever you do different, ideally should improve that solution. And considering how long this problem has had attention and solutions, I think it would be non-trivial to try to beat the state of the art, which is why I'm suggesting including that as a step in a pipeline that does something.
Okay, so
Yeah, so what did you have?
this is going to use these 4 techniques and show the progression. So I would first go with OpenCV and see how that improves the image deblurred, the error in the deblurred image.
Okay.
And if I would use if I have to use object detection to show that it is helping face detection,
Hmm.
so I could just use a face detection API and use it to show that it does help. Is that
API, what do you mean?
because
Are you
you
talking about
have
like
to
a
focus-
Cloud Vision API or something like that?
yeah, something
Mm,
like an API to do face detection. Because
Yeah, you
said
can use
that-
a pre-trained model or something.
Yes.
Whatever you're
Something-
doing, the computation has to be like within the same code.
Yes.
So if you're sending it to the cloud, you can't do that. Deep learning, I think I must have said, yeah, so I said recognition over detection, because in recognition, you care about the identity of the individual rather than just detecting a person. So for detection, you don't really need finer features, right? You just need a general sort of vague representation match to find a person. But if it's recognition, then that's the kind of thing where the finer details come into play. So something like deep learning might help, especially if it's for CCTV or maybe like sports footage or something like that. You want to keep track of which player the camera is focusing on while they're running. You could try deblurring frames.
I could also switch the project to a different area.
If you're doing that, then it has to be a robust idea and you come up with it sooner rather than later, because time spent switching and picking topics now is time that you have, less time that you have to implement the actual project. If you do decide to do that, send something by this Saturday or Sunday. Email it to me directly. Cool, yeah, keep me posted.
Thank
Yeah, you're welcome.
You asked, so the grading scheme is if it's 90 plus, then it's A plus or what?
The final letter grade, that I'll decide based on what scores everyone in the class is getting. And I'll be discussing with Dr. Rata, who taught this class earlier. So generally, I think his class pretty much, most people get between an A to B plus usually. And I'm going to be doing something similar. I'll just take all my scores and trade notes with him.
Okay. The quizzes, so I'm not exactly sure how much that would constitute. So I think it's
2.5% per quiz. I'll be taking 4 best quiz scores out of 5.
okay. Thank you.
You're welcome. Hey,
I saw your feedback
soccer, I remember.
too,
Yeah.
like, would be kind of cool. I found, I have, I think I mentioned, I found like a package that works pretty good for like the post detection.
Hmm.
So I saw you said, I liked your idea of using like the.
I don't
for the sound.
remember what I said.
Yeah, you said.
Oh,
sound.
yeah.
So is there any use in using like multiple frames, or should I just try and stick to one?
I would definitely recommend starting with 1 frame, and then if you still have the time, you can probably add maybe 5 frames leading up to it and use something like an LSTM, which is designed for sequences and time series. So that might improve things a little bit, because you could hypothesize that that would implicitly let you model the physics going on in like leading up to the kick.
Gotcha. Oh, so my idea, just for like, for simplicity's sake, I was gonna try and start by just predicting like whether a shot would be like on target on the net at all.
Yeah, yeah,
Does that seem like the?
Yeah,
spot to start?
because it's a broader goal.
Mhm.
And it would be easier to predict whether it'll end up inside the rectangle or outside. Yeah, that's a
Okay. and
good
then I
way
can-
to start it.
then I can refine it.
Mhm.
Works.
Yeah. Hi.
You propose this without counting using
Right.
unit. So, I'm not sure what you wanted to discuss about it. But
What feedback did I give you?
I wanted to motivate why using swing unit is better.
What is- Yeah, I mean, this is not what you told me initially, right? When
Yeah,
we spoke about
okay.
it. Why did you choose this?
I wanted to try out like transformer with unit architect for segmentation,
Mm.
but you gave the idea of calculating, I mean, doing census in underwater images.
Mm.
So I thought this will be better in this case, where you can count number of people in a crowd. Crowded
Okay.
areas.
And uh, so this approach no one has taken so far?
No one has used swing transformer yet.
Okay.
In this architecture swing unit for this approach, but I have seen clip-based approaches to count.
Okay, so why Swin unit then? That's the
Swing-
only remaining question.
I feel like swing has like, because it moves the window, it can be invariant to scale.
Mm.
So it can capture features like, for example, for example, in an image like this, like you will have the window size matters, right, for each in-person
Mm.
image.
Okay.
So I think Swing will be better, Swing transform will be better for images like this, where we'll be able to capture facial details like at different scales.
Mm.
And since I want a pixel level classification, unit will be better combining with that.
Okay, so that's an argument for shifted windows. Why unit?
Yeah, that's what, since we have pixel level representation for if there's a face in each pixel,
Mm.
because that's how the data sets are annotated. Like it gives
Okay.
XY coordinate for each, if there is a person's face detected in that pixel,
Okay.
kind of like center point for a face.
Okay, yeah, makes sense.
So
Go.
unit probably makes sense because I want to classify it. So that's what one thing that I'm not unsure of is to predict the XY coordinates of a face or
Mm.
compute a density map.
Mm.
Because all the state of the art approaches that I have attached predicts the XY points.
So they all predict pixel
Pixel.
labels?
Yeah.
Okay. Yeah, I mean, that's a choice for you to make depending on.
What do you think is better?
I think a density map would be a lot easier to do, but try the other one first, and if it doesn't work, then fall back to
Yes.
a.
So what do we?
I just wanted to know your reasoning behind choosing this particular architecture. That's all. I don't
because
have
this
any.
swim unit is extremely popular in
Mm.
the med segment, biomedical image segment. So why not use this for this?
Yeah, yeah, it's good for fine-grained stuff. Okay, yeah. Go ahead.
What do you think for the final proposal? Like,
Refined proposal, I guess just talk about all the things you told me just now, why you think that this is a good solution, basically. So you want to justify whatever it is you're doing, right? To
Yeah.
justify that the things that you care about is whether anyone else has already done it or not. That's why your literature survey part comes in. You know that no one else has done this. based on the nature of the images that you aim to be dealing with and the nature of the problem, you think that multi-scale feature extraction would help. And that's something that existing solutions aren't taking into account. So the SWIN aspect comes into play over there. And then since you're trying to predict pixel labels or classes for each pixel, then a segmentation style approach is good for that, which is why SWIN unit. Yeah, that's more or less it. Yeah, you're welcome. Hi. What was your idea? What feedback would I give you?
We were trying to do like style matching.
Oh, right.
Style
Yeah. Style transfer, I mean, it's been around for a while, right? And there was a whole, I forget what the app was called, Prisma. And I mean, there's a lot that's been done there already, which is why I wanted you to like add something to it.
So,
Could you please explain the feature?
So basically, your full script would consist of the style transfer part. Style transfer, I think now it's a lot faster than it used to be back in the Prisma days where you had to keep doing it for a lot of iterations. I think with diffusion now you should be able to do it a lot faster. Maybe. I'm not sure how fast it is. You'd have to see, but look at the whatever is has a lot of stars on style transfer and is relatively new. Maybe look at 2022 and later.
He said,
So
emotions.
right.
Guess style.
So I was saying, you pick an initial style at random, say Van Gogh or whatever, right? You take an image, convert it to have, let's say, 6 initial styles that you can start with, and pick one from those at random, convert your image to that style, and also have your webcam running and do emotion recognition on your face. So the output that you get from emotion recognition will typically have some mixture of, say, happiness, anger, disgust, whatever. And you can use that to guide your style. So modify your style, what is it, the gram matrix or whatever is used to sort of condition your output in terms of what style you're looking for.
Let's say we got a mixture of happy and sad and angry. So initially we took some Van Gogh style. We showed the users Van Gogh style, and in response we got sad and angry. So how would the Van Gogh style change based on emotion? So what kind of so
just randomly tweak your style input and generate something new, see what new emotion you're getting, and just log all of those readings, emotion readings, and your style matrices, and you can calculate gradients for emotion to show which emotion you're heading towards based on what changes you're making to the style. You see?
tweak the lifestyle is in each emotion in place, and with the style. The metrics as happiness. Is that what you? No.
Yeah, I'm not saying necessarily like maximize for an emotion or anything, but you can use that to take style transfer and make it an interactive human in the loop kind of process. So that there's um
And what kind of output are we expecting while we are including emotion? Are we just trying to detect the emotion?
yeah, you don't need to do anything extra with it. So your flow chart, if I had to make one, would look something like, let me think a little bit. This is your style transfer. You have an input image, which also accepts some sort of a condition. I think that's how style transfer works, because you need to give it a target style, right? So I'm calling that the condition, including that, and this generates your transferred image. In addition to this, you also do emotion recognition, which looks at, it's called this face. This will spit out some sort of a vector, which will be your probability distribution over all classes. So let's call this V1. So you generate one image, then you look at your face. So at this point, you have your transformed, style transferred one, you have V1, and you also have your original condition, whatever it was. Then what you do is perturb this to just randomly change it somehow, apply that to this image, and you get I2, and you also have a V2 at this point. Then you look at how it changed. So this is your gradient effectively, and this will head towards a certain emotion. And you can choose one of these as your target. Maybe you want to elicit happiness from people who see your transferred art. Just set that as your target, and if it is improving towards that, then look at how C1 changed from C0, the difference. So that gives you the direction in which you changed each element in your condition, right? And just keep making changes in that same direction. So direction, it doesn't really make a lot of sense if you have a 3x3 gram matrix, or however the style is represented, but you don't need to be able to conceptualize direction directly. Just that if you think of it in terms of gradients, then you will get some direction. I don't know, it's just an idea. Do,
Maybe.
does it make sense?
Yeah. Possibly maybe we can be creative in this part, like after we receive this
Emotion.
yeah, after we receive emotion, based on emotion, we can do some modification to the original style, be creative, like,
Yeah, so there's this artist, Bekshinsky. His artwork is like it elicits dread, and that's the feeling that he goes for with his art, right? So you can sort of automate that basically.
And one more thing, like, this proposals are graded or project proposals.
Yeah, but it will be a, a, 'small part of your overall project grade. Oh,
But if you don't submit it, then you would lose 10% overall.
Hmm.
Even if you don't submit it. So that's it on.
don't worry about it.
Okay, so the reason we have lost 5 marks, so we just want to know like.
In the grand scheme of things, that 5 marks is nothing.
Yeah, that's it.
Yes,
So regarding the image in painting, like
in painting, yeah.
so it's an end application.
It is I mean, it's a whole task of its own, sure. It's self-contained. But the problem with picking just a single task is that other people have done it already. And the approaches that are the state of the art are likely approaches that people have spent at least a year, couple of years developing. They've probably been working in that domain for like a decade. So it would be hard to build something novel. What was the feedback I gave you? Mm, mm, Yeah, so state of the art, what you have in here is from 2018, 2019, and in painting, I think today with diffusion and all of that, they probably do something diffusion based. I'm not sure what the state of the art is, but I know that it'll be more recent than 2019. So these are the models that are doing the best so far. And odds are these are pretty recent. So if you pick, okay, this is from like 22. Basically, my concern was just that you should be doing a bit more literature review to find what the actual state of the art is. Because if you pick something older, what is it you're proposing to do here? Just high level in a sentence with.
There are like few techniques, like there was like adversarial GAN approach in this
Mhm.
for the edges kind of thing, edges detection. Like when you paint, so you have to actually find the correct edges in order to paint something, or if you want to remove an object also. So it was like edge detection was most focused here,
Hmm.
and this was more like the painting thing, general painting thing. I thought of like combining both of them in order to make like more robust kind of model.
So detecting edges first is a necessity only because of the way that those particular approaches of that time were formulated, where you first find where you have to plug it in. Instead of that, if you formulate it as a diffusion problem or an autoencoder style problem where you learn a distilled representation of it and then generate it back, that will automatically fill in whatever missing information, since it's learning a semantic version of the input space, and then generating that using a description. Like if you say, oh, well, there's a classroom that has however many rows, there's two smaller rows on the side, you can already start imagining what the room looks like, right? So that's the kind of like joint language and visual approach that most problems are being solved with today. So when you're doing things like that, these sort of problems go away. So then an approach that is solving an approach that is addressing a research gap in those is not really, it's hard to sell that, right? Which is why I'm recommending not picking a single task and trying to find a better solution than what is out there, but combining existing good solutions for tasks. So you perform multiple tasks, and it's easier to find combinations that no one else has thought of than to like innovate a method that no one has thought of.
Like, what would you suggest where we could like,
Uh,
in general sense, we could use it for creating the sample images or kind of thing, which is kind of creating a training data or as such. But
hmm,
where exactly,
in painting, I'd have to think about it. I don't have anything off the top of my head. But yeah, I mean, I guess just read a bit more, see if you can add another step.
we'll come up with something. Yeah.
Yeah, I don't want another like whole document like this, but just whatever you come up with, email me or do a private post on Piazza telling me what your like functional steps in the pipeline are. Is this like were you?
Create some other application or use it in some other.
Mm, maybe like no, I mean that's a pretty trivial case. I was thinking like there's Photoshop requests where people say get this photo bomber out of the picture, but again that's the same like segment anything does that, and content aware filling is something that Photoshop does, and I think Google Photos also does on the Pixel. So that's a combination of a few things, right? It's segmenting to find what to remove, and it's also figuring out what to plug in, which is in painting. If you could think of maybe one more step that you can add to that, then I think that would be sufficient, because if not, then you're just re-implementing. I mean, yeah, I guess it would be okay if you are able to get rid of something and do content aware filling, because that's two tasks. I'm just not very enthusiastic about that since it's already like commonly available, but there is value in knowing how to do it also. So I don't know. I guess as long as it's not just one repo for segment and thing that already has all the inference and everything examples done. If it's not like that, then I think that would be fine. But from what I'm aware, segment anything, I think that already has content aware filling also.
Yeah, one.
Hmm. Yes, look into it a little bit, think, get creative. If you want to change your topic, you can still do that. Just sooner rather than later. Don't waste a lot of time on this. Uh, Send me something over the weekend, preferably, like by Sunday afternoon. It's not a hard deadline. I'm not going to penalize you or anything. It'll just be better for both you and me, because I'll be able to look at it in time and give you feedback.
Thank you.
Welcome. More questions?
Yeah, one just.
So I have this visitors pass. I posted on Piazza on Thursday. I didn't come.
All right, yeah. How are you now?
I'm good. Feel better. Yeah.
Yeah, I can consider yours. I don't need to see her.
Okay.
Yeah. that's
You're
it.
fine, all good.
Yeah. Still like have to go for other appointments. But I'm good.
Okay. Yeah, if you need anything, let me know. Right. Welcome.
First, what you have to think.
Uh, what was the full feedback?
That I think you wanted to do us with application oriented.
Hmm. Your name is Rupesh. What's this is sorted by last name? What's the last name?
Vinod Kumar.
Okay, so it's on the next page. That I hope it didn't come across like a you're in trouble, meet me after class type thing. I just wanted to yeah, okay. I mean, I get why calibration is important, but it's already been done a fair bit, right? There's good solutions for it, so why reinvent the wheel? What are you suggesting doing exactly? Just implementing it?
So just want get up instead of almost driving. I thought of doing light and camera calibration for the object.
What you could do, I guess, is do you have access to a LiDAR camera?
No, we thought of getting a data set from the wave or open source.
Okay. Do you have a robotics? Do you work with any labs or?
Yeah, I started to work with the process. No challenge.
Yeah.
I work with. I started to work. On
What are you working on?
I'm working on the same camera part.
So they have LiDAR and
Yeah,
you're
they have
working on
LiDAR.
LiDAR. How much freedom do you have with the hardware?
Just started like last week. For now, I have like restricted, but I can capable to get the data. I have access to that.
Okay, yeah, I mean, if you have the option of using some of that data for this, check with them first. Then what you could do is, I don't know, maybe do SLAM with it, uncalibrated and calibrated, and compare. But I mean, that's just still only for calibration. Maybe you could do just one simple thing you could add to it. You know how I don't know if it's a thing on Androids also, or whether you use an iPhone or not, but there's the measurement app that
Yeah.
uses
I-
depth. So if it's not calibrated, whatever values you get are obviously going to be wrong. Maybe you could build a simple like visual equivalent of that. It doesn't have to be like very sophisticated AI sort of thing, but because then you'll be using the calibration that you're doing downstream, right? And I think it's simple enough to do.
So earlier, what we have is a target calibration, right? We use the check output for that. But nowadays, the people are coming with the targetless for the automatic thing. You don't have to manually select the cloud point to the corresponding data.
Okay.
What I thought is doing it in the using the machine learning thing, automatically selecting the feature, which might be very easy for machine.
Wait, so
So basically, what we have like in the target,
LiDAR calibration so far, state of the art, is doing it without a target. Is that a thing already? Has it been done?
yeah, it's been done. Yeah, they have
Okay.
things for that.
What so you're saying they use some set of features for calibration that
Yeah, they use a natural features that just like a edge or corner.
Oh, okay. And you want to use, you like come up with,
Like machine learning thing to get a natural target, maybe.
okay. If that hasn't been done, then that's a great idea. You could even publish it if it works.
But I need to do research. Even I'm not sure.
Hmm. Okay. Yeah, I mean, it's worth looking into. Yeah, as long as you're confident that you can do this, it's a good project. So read up on it and tell me if you want to stick with this or change. That's all.
So you have the liberty to change before 5th of July.
I mean, if you think that sticking with what you have right now is definitely bad and you're not going to be able to do it, then of course change. I'm not placing any like hard restrictions on whether you can change your topic or not, but just keep in mind that you only have the rest of the semester to finish it, and that's why I'm pushing to lock your topics as soon as you can. So yeah, just read up on it and let me know what you guys want to do, whether you're confident about sticking with this or what changes you want to do. As long as you have some sort of a plan and a roadmap of what you're going to implement, and it sounds like you know what you're doing, that'll be fine. Anything else?
That's it.
Okay.
We'll mail you.
Yeah. Good luck. Oh, well, what did you think of the quiz? Was it unfair or reasonable?
It was so too sudden for us. We didn't know that it would be.
Yeah, that is intentional.
At least if we would get to know the syllabus ahead, it would be more helpful because I was thinking it would cover maybe up to machine learning like the last quiz, but then it was just one chapter.
Machine learning and the other stuff, it's kind of unrelated, right? There's no like smooth transition between them, which is why I didn't put that. So I'll be doing the two machine learning classes and neural networks and CNNs probably together. I don't know. It also depends on like how dense each topic is and how many questions I want to ask. But in terms of just like difficulty of questions, what do you think?
It was fair enough.
Last day of class. So that is 26th of August, I think, or 16th of August. Whenever the last class is.
I saw it's 15th August.
Yeah, then it's that.
Can we get to know the syllabus before the quizzes are conducted? We
No.
don't have to know the quiz dates. We just have to know the syllabus, like what would be included in the quiz.
So typically, whatever I'm currently going over in class, I don't cover that. So from the same week, I'll never put anything in a quiz. Uh, up to a week before usually. In this case, initially I was planning to put the first two ML classes also, but it just felt like a lot, and I wouldn't be able to spread questions across all topics. So yeah, I can't tell you what topics I'm going to put because I decide as I'm coming up with questions. And I mean, the kind of questions that I put in here are mostly like things that you can say verbally, right? So as long as you review your slides enough that you can like vaguely explain it to someone else, then I think you should do fine on quizzes. Okay. Welcome.